This is section 3.5, rational functions, and we're going to begin with applying notation that describes the infinite behavior of a function. Okay, so if we have a rational function made up of a quotient of polynomials, so p of x in the numerator and q of x in the denominator, they are both polynomials. The notation is this: x approaches a constant coming from the right, but will not equal that constant. X approaches this constant coming from the left, but will not equal that constant. And then we have x approaches infinity and negative infinity. And this is where the function, as the x approaches positive infinity, so that is where x is increasing without bound and x is decreasing without bound. So this is what this very important notation means. Okay, so let's complete some statements using this notation. So the graph of f of x equals x minus 1 divided by x minus 3 is given. Complete the statements. As x approaches positive infinity, so that means if x gets very, very large without bound, it's asking you what are the y values doing. And as you can see, the y values are approaching 0. Approaching 1. And you can see right here, that line. So that's where the y values are going. They're going down, 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 down towards 1. Okay, as x approaches negative infinity, you can see how these y values are getting very close to negative 1. And we are approaching 1 from above. And we are approaching negative 1 from below. Okay, now let's approach a value. So, as x approaches 3, coming from the right, so the x's are getting very close to 3. Look what those y values are doing. They're going to positive infinity. And you can put a plus in front if you want. As x approaches 3 coming from the left, those y values are going to negative infinity. Okay, in order to identify vertical asymptotes, we really need a good definition of vertical asymptotes. So the line x equal to some constant, you can see there it is, there it is. All of these vertical asymptotes. How can we define a vertical asymptote using this notation? Well, it says if the y values approach infinity or if they approach negative infinity, as x approaches c from either side. So let's take a look at this. We're going to approach c coming from the right, and as you can see, the y values approach infinity. Okay? As we approach c from the right. Now, if we approach c from the left, it says we're going to go to positive infinity as well. So we're going to approach c coming from the left, and the graph goes to positive infinity. Now, what if we approach c coming from the right, and the y values go to negative infinity, and likewise will look like that. Okay? So let f of x be a quotient of polynomials p of x and q of x that have no common factors other than 1. to locate the vertical asymptotes of f of x, determine the real numbers x where the denominator is equal to 0, but the numerator is non-zero. Okay? So we're going to look at number 2. As you can see, this function, you can factor this denominator, and we have x minus 5 multiplied by x plus 1. So we know that x equals 5 and x equals negative 1. Those are our 2 vertical asymptotes. Okay, looking at number 3, we have x minus 3 in the numerator, but then we have x minus 3 multiplied by x plus 1. And as you can see, we can cancel the factor x minus 3 out, and we're left with 1 divided by x plus 1. So now we can say that we have a vertical asymptote at x equal to negative 1. Okay, we do have a hole at x equal to 3, and I think it's worth mentioning. So there is a hole in the graph at x equal to 3. When you cancel a term, there is a hole. Okay, let's look at number 4. And in number 4, we have f of x equals negative 8 divided by x squared plus 25. Well, if we set that denominator equal to 0, there are no vertical asymptotes. That's not a real number. Okay, now let's talk about horizontal asymptotes. So the definition of a horizontal asymptote, y equal to d, of the graph of a function f, if f of x approaches d as x approaches infinity or negative infinity. So if f of x approaches some number d, we have y equal to d as a horizontal asymptote. So let's look at case number 1. And case number 1 is as x approaches positive infinity, the y value is approaching d. So y equal to d is a vertical asymptote. We can also approach positive infinity, and you can see y equal to d is also a horizontal asymptote. My goodness. Horizontal asymptote. So now if x approaches negative infinity, we could have y equal to d is a horizontal asymptote. And we can also have we can also have x approaches negative infinity and y equal to d is a horizontal asymptote. Okay, so now let's just say we have our function definition, and this is the general form, of course. How can we find these horizontal asymptotes? Well, we are going to be looking at the degree of the denominator and the degree of the numerator, and we're going to compare those. So the degree of the numerator is n, and if that is greater than the degree of the denominator, there are no horizontal asymptotes. If the degree of the numerator is less than the degree of the denominator, then the line y equal to 0 is a horizontal asymptote, and that happens to be the x-axis. And if the degrees are the same, we will make a ratio of the leading coefficients. And that is going to be our horizontal asymptote. Okay, let's take a look at these. Look at number 5. And in number 5, what do you notice? The degree of the numerator is less than the degree of the denominator. So just looking at these degrees, I have 3x over x squared. This is degree 1. And I guess they said m is 2. So here, n is less than m. So we have y equal to 0 is a horizontal asymptote. Okay, let's look at number 6. We have n equal to 2, and we have m equal to 2. So these degrees are the same. So we have to make a ratio of these coefficients. Y equals 3 over 1, or y equal to 3 is a horizontal asymptote. Okay. Now, looking at number 7, we have the numerator has a degree of 3, and the denominator has a degree of 2. So here, n is greater than m. So there is no horizontal asymptote. And you know, I didn't write that out here. N is equal to m. Okay. So you can see each one of these graphs for number 5, 6, and 7 below. If you would like to see y equal to 0 is a horizontal asymptote, and we've got y equal to 3 is a horizontal asymptote, and we have no horizontal asymptote in number 7. Okay, the graph of a rational function may not cross a vertical asymptote. However, the graph may cross a horizontal asymptote. So how can we tell if the function is going to cross its horizontal asymptote? Let's first find the horizontal asymptote. So we're going to find the horizontal asymptote. So we're going to look at the degree of the numerator, and we're going to look at the degree of the denominator, and both of these degrees are 2, so n is equal to m. So what do we have? Y equal to 2 is a horizontal asymptote. Okay, so now determine if the function crosses its horizontal asymptote. So we will set the horizontal asymptote equal to f of x, and we will see if we can solve for x. Okay, so we're going to set 2 equal to 2x squared minus 4 all over x squared minus 3x minus 4. And now we'll multiply both sides by that denominator. So we'll have 2x squared minus 6x minus 8 equals 2x squared minus 4. And then we get a negative 6x minus 8 equals a negative 4. And we'll just keep solving this. So x is equal to a negative 2/3. So therefore, yes, f of x crosses y equal to 2 when x is equal to, or how about at x equals negative 2/3. Okay. So now we're going to identify a slant asymptote, and we have a slant asymptote only if the degree of the numerator is exactly 1 greater than the degree of the denominator, okay? So, to find an equation of a slant asymptote, we will divide the numerator of the function by the denominator. And that quotient that is remaining will be linear, and the slant asymptote will be of the form y equals the quotient. So as you can see here, the degree of the numerator is 3. The degree of the denominator is 2. Since this is the case and is exactly 1 more than m, we have a slant asymptote. How are we going to do this? We are going to divide the numerator by the denominator. And so we can have 3x cubed divided by x squared minus 9. And we can multiply this by an x, so we have x cubed minus 9x. And then we have 10x. And then we cannot, let's see. Oh, I messed this up here. Minus, yes, 3x squared. Should be a 3x. And we have a 3x cubed minus 27x. And subtracting these, we have a positive 27x. Now this is our remainder. And we don't use or consider this remainder. We only want this 3x. So y equal to 3x is the slant asymptote. And you might also hear this called an oblique asymptote. Okay. So now let's talk about when we want to just graph these rational functions. What might we do? Where would we begin? Well, if we're going to graph these rational functions, the first thing we probably want to do is we want to find the intercepts. That's both the x and the y. And then find those asymptotes. We'll find the vertical asymptotes first, and then the horizontal asymptotes. Then take a look at symmetry, and then we could plot some points if we needed some extra help with graphing. So starting with number 1, let's start with our intercepts. So to find our x-intercept, we will let y be 0. And then and this is actually a typo. This should say 6. Okay? could actually maybe write that a little bit better. Okay, so now if we have this set equal to 0, we have x minus 3 multiplied by x plus 2. And so we have that x is equal to 3 and negative 2. And so these points here are 3, 0, and negative 2, 0. Okay, so now let's look for our y-intercept. And that's when we let x be 0. And we come up with y equal to 1. And that point that's generated is 0, 1. Okay. And I think that's supposed to be 10. So maybe 0, 1 would be right there. Okay. Now let's look at the for the vertical asymptote. And that's when we set that denominator equal to 0. And we come up with x is equal to 6 and x is equal to negative 1. And those are our vertical asymptotes. So x is equal to 6. And I think these were graphed at the wrong place. So this would have been 3, 0. And negative 2, 0. Okay. And now let's graph our vertical asymptote. X equal to 6. Oops. Well, and x equal to negative 1. Okay, so now let's take a look at our horizontal asymptote. And as you can see, the numerator's degree is 2 and the denominator's degree is 2. So when those degrees are the same, we make a ratio of those coefficients and we get y equal to 1. Okay, so now let's check for symmetry. So let's plug f of negative x into the function and we'll get x squared plus x minus 6 all over x squared plus 5x minus 6. Well, that is definitely not equal to f of x, and that's definitely not equal to the opposite of f. So therefore, there is no symmetry to the y-axis or to the origin. So the only other thing we might want to do is we might want to plot a few points. We might want to check some points. And I say that because, first of all, this graph, if it has to have these asymptotes, will look like this. And we really need to find a point in here and a point somewhere in here. Now we also know that the graph is going to do that, but it just might be nice to get some points. So let's make a little table. And as you can see, we have x equal to, let's say, -3, 4, and 7. And that kind of gives us a point here and at 4 and 7. So in all of those little areas, and it can tell us where these, where this graph crosses, okay? So when x is -3, y is 1/3. So that is why we're right here. And when x is 4, y is a -0.6. So we're right here. And when x is 7, y is 4.5. So about right here. So now we know that this graph looks like that. Okay, let's try number 11. And in number 11, we're going to do the same thing. We're going to begin with the x-intercepts. And we have our first x-intercept at the origin. And then our y-intercepts. And that's in the same place at the origin. Okay, now let's talk about the vertical asymptotes. We're going to set that denominator equal to 0. And we come up with x equal to 2 and x equal to -2. And now let's look for the horizontal asymptote. And that degree of the numerator is 2 and the degree of the denominator is 2. And so we have y equal to 2. And so now let's look for some symmetry. And for some symmetry, we will find f of -x, and that's 2x squared over x squared minus 4, and that's exactly equal to f of x. Therefore, the graph is symmetric to the y-axis. So now let's find a few points in each little area, and then we'll be ready to graph. So now, if we have some points, and we can have x and y, we have -1, -3, 1, and 3. And if you plug these in, I'll just go ahead and give you these, but you can check those. And if we get these on the graph, if we're at -1, -2/3, and -3 and 3.6, and 1, -1/3, and then 3, 3.6. So now you can see we have that symmetry with respect to the y-axis. And there's our graph. Did not do a very good job there. Okay, let's take a look at number 12. As you can see, we have Well, we'll begin with our x-intercepts. That's when we let y be 0. And we come up with x is equal to 2. And that point that's generated is 2, 0. See, 2, 4, 6, 8, 10. I guess we could just use this as 10. I don't know how we're going to get 15. I guess each hash mark is 3. So we'll have to do that. So we have 2, 0 would be right here. And then let's go ahead and get our y-intercept. That's when we let x be 0. And we get negative 8/3. Okay. And then now we can look at our vertical asymptotes. Set that denominator equal to 0. And then the horizontal asymptotes, there are none. Since, I'll go ahead and write that out, since the degree of the numerator is 2 and the degree of the denominator is 1. So there are no horizontal asymptotes. However, we do have a slant asymptote. So we will take x minus 3, and actually we could use synthetic division here since we're going to divide by x minus 3. So we could put 3 in the box. And let's take a look. We have a 2, a negative 8, and an 8. We will get rid of the remainder. And this slant asymptote is y equals 2x minus 2. Okay, and then let's check symmetry. So if we have f of negative x, that's 2x squared plus 8x plus 8 all over negative x minus 3. And that is not equal to f of x, and that's definitely not equal to the opposite of what we started with. So there is no y-axis or origin symmetry. Okay. Now just taking a few points. And that would be in each one of these areas. We could try negative 3, negative 1, 1, I don't know, 4 and 5. Let's try those. And plugging those in. And if you need to find those and pause the video, you can. So if we have negative 3 and negative 8.3 and negative 1 and negative 4.5. And I did not plot our slant asymptote. We need to plot this. So that is y equal to 2x minus 2. So it goes through about right here. And then it has a slope of 2. So it would go kind of like this. Okay. So now you can really see where these points are. And then we have 1, -1. And then 4 and a +8. And then 5 and a +9. So as you can see, these are the graphs. That is the graph. Okay, wonderful. Let's take a look at how we would use transformations to graph this function. Well, if you started with the parent function, f of x, or just start, we'll just write y equals. And then you would start with this, and then you would go to the right 3. So now the new vertical asymptote is x equal to 3. And then you would shift down 1, and the new horizontal asymptote is y equal to -1. And I say this because this parent function has an vertical asymptote here and a horizontal asymptote here. So we're actually shifting the horizontal and vertical asymptote of the parent function. That's actually what we're doing. So now we will go down 1 and to the right 3. We have something that looks like this. So transformations is a nice way. And let's just try an applications problem using rational functions. And we have Young's rule as a formula for calculating the approximate dosage for a child given the adult dosage. For an adult dosage of D milligrams, the child's dosage may be calculated by this function. Okay, and X is the child's age in year between 2 and 13. So what is the horizontal asymptote of the function? So the horizontal asymptote is dx over x. So the horizontal asymptote is y equal to d. And basically the child dose will approach the adult dose, but never equal it. Okay, and so what is the vertical asymptote of the function? Well, we'll take that denominator and set it equal to 0. So we have x is equal to -12. And for an adult dosage of 50 milligrams, what is the approximate dosage for a 9-year-old child? Well, this is d equal to 50. And we have c of x is equal to 50 times x divided by x plus 12. Well, now we want to find c of 9. And we'll get approximately 21 21.4 milligrams. And this is actually what the graph looks like. And as you can see, we have D equal to 50, and you can see that the Y value when X is 9 is going to be about 21.4. So you can see what this function looks like on the graph. And that concludes this section.